Alright, good afternoon, Year 10. I figured because we have now done some work on reaction types, it is worthwhile to now go through some of these activities and discuss the thought process behind the solutions. So on Monday, May 4th, that lesson was designed to start introducing us to the different types of reactions. And the goal for the lesson was to explain the benefits of classifying reactions and identify composition and decomposition reactions and give examples. So to achieve these two learning goals, there were a series of activities. So let's start to go through them. So the very start of this unit talks about why do we actually classify reactions? And it starts off with a little bit of theory saying the image above shows an abandoned saltpeter refinery in Chile. Saltpeter or potassium nitrate, KNO3, used to be the world's main source of nitrogen-based fertilizers. But all of that changed in the early 20th century when a German chemist discovered a new way of producing fertilizers. So that abandoned saltpeter refinery that's mentioned there is just this image up the top here. You can see it's looking a bit old, so because it is abandoned, it's no longer in use or occupied ever since a alternate method of producing potassium nitrate was generated. So first of all, there's a quick clip here for you to watch. I'm not going to play it for you now. You can pause this recording and watch this video in your own time. But after you watch that, the first activity asks you to just take some notes from the video, whether it is something you found interesting or something you're not too sure about, but this space was designed for you to just jot down a few notes that might come in handy a bit later. Then it goes on to explain, in addition to fertilizers, ammonia is used as a reactant to produce many other useful chemicals, such as pharmaceuticals or household cleaners. It's also a key component in many explosives. During World War I, the Haber process allowed Germany to continue producing large amounts of explosives after Allied forces blocked the supply of saltpeter from Chile. Just below it, there are a few images where the caption tells us that many of our most useful materials have been created by controlled chemical reactions, including plastics for our containers, medicines, shown in the center, or even the batteries that power all of our devices. Understanding chemical reactions give us enormous advantages. It helps us explain and predict changes in the natural world and also allows us to create useful synthetic materials. Because chemical reactions are incredibly diverse, one way to get an understanding of them is by looking for patterns amongst them. This allows us to classify them into types based on common characteristics. You may have already learnt about some of these types, such as combustion reactions and acid-base reactions. So far, Year 10, we have looked at combustion reactions, not so much acid-base reactions. We will get into a bit of that later this term. Activity 2. You're asked to classify, or you're asked a question and whether it's true or false. So classifying chemical reactions according to the years that the reactions were discovered helps chemists understand how the reactions work. So what we were looking for this one here is actually false. And the reason for that is that the year of discovery is usually unrelated to the nature of the reaction. So this way of actually classifying the reactions does not help us at all. It is actually quite useless. Question 3. Classifying reactions according to common characteristics help build understandings and explains how the reaction works. The answer for this one is actually true, and the reason for that is by grouping reactions together by features they have in common, scientists actually gain a greater understanding of how different types of reactions work. So I'll just show the answer for these ones here. The next part here. So across the next two lessons, we will be looking at the composition reactions and decomposition reactions. And the following lesson would have been on single displacement and double displacement reactions. Now, a little bit more about composition reactions. So earlier it was mentioned, the Haber process was mentioned. So the Haber process is an example of a composition reaction, also known as a combustion or synthesis reaction. All of these words, composition, combustion, and synthesis, means to create or to combine. So in this type of reaction, two or more reactants, so starting materials, join together to form a single product. So this part here is very important. The general form is given by the following equation. A plus B gives you AB. So reactant A plus reactant B reacts together or combines to form product AB. So Haber knew that to produce ammonia, NH3, he would need to chemically combine the elements hydrogen, H, and nitrogen, N, both of which form diatomic molecules, which means they are atoms that exist in pairs. So, given what he realized, with the nitrogen gas and the hydrogen gas to produce our ammonia gas, what he ended up having to do is your nitrogen exists as a diatomic molecule, so there's 2 lots of nitrogen gas given by the G. He reacts it with 3 lots of hydrogen, H2, gas to produce 2 lots of ammonia gas. So all these letters in these brackets, so the G, and the G, that represents it's a gas. If it was a liquid, it would be shown with an L. If it was a solid, with an S. Or if it was if it was a solution that was dissolved in water, it would be shown with an AQ, which represents aqueous solution. Given what that little paragraph there explains to us, you're then asked, in the Haber process, how many molecules of hydrogen are needed to react with each molecule of nitrogen? So, if we scroll back up here, what we are told is we have 1 lot of nitrogen gas reacting with 3 lots of hydrogen gas to give you 2 lots of ammonia gas. So the answer for number 4, how many molecules of hydrogen? What we would be looking for is 3, because in front of the hydrogen gas, there is a number 3. Number 5 here. According to the video that was shown up at this very start, why was Haber's discovery so important? What we were looking for here is that it was important because it allowed the production of fertilizers that make it possible to feed 7 billion humans, in contrast to the 4 billion we could feed if we didn't have the fertilizer. So Haber process was really important for the development of fertilizers. As we're all aware, fertilizers help us with our crops, and when it comes to harvesting, it means there is a higher yield, so we can end up with more product, so we can actually feed more people. So 4 billion in comparison to the 7 billion humans that we could feed. Now, number 6. Which of the following is a composition reaction? Keeping in mind that a composition reaction is when 2 or more reactants combine together to give you one product. So keeping that in mind, we can automatically rule out anything that has 2 or more products. So for example, the hydrochloric acid plus magnesium gives you hydrogen plus magnesium chloride, so it cannot be that. It cannot be this one here, where you have water that produces hydrogen and oxygen, because that tells us there are 2 products, and we know we have to end up with 1. And we also know that it cannot be sodium chloride plus silver nitrate, because that gives you 2 products once again. So what you're looking at is iron plus sulfur gives you iron sulfide. So if we look at the general formula, it is A plus B gives you AB. So that would be the answer for question 6. Question 7. Which one of the following is a composition reaction? So it's similar to question 6, but instead of the word equations, we are given the chemical equations. So still go through it using the same thought process. A plus B gives you AB. So it cannot be the first one here because you've got 2 products. It might be this one here because we've gone from 2 reactants, so H2 gas plus Cl2 gas, giving you 2 HCl gas. It cannot be this equation here because you end up with 2 products. And it cannot be this last one here because you end up with 3 products. So 1, 2, and 3. So that tells us it has to be this one up here. So 2 reactants giving you 1 product. So A plus B gives you AB. Question 8. One way of protecting iron or steel from rusting is by galvanizing it, that is, coating it in a layer of zinc metal, Zn. This then reacts with oxygen, O2, in the air to produce a protective layer of solid zinc oxide, ZnO. Write a word equation for this reaction. You can copy and paste this arrow here. So, given the information in this paragraph here, we know that we must react zinc with oxygen to give us zinc oxide. So what that would mean is you have, as the word equation, we've got zinc, we then react it with oxygen to give us zinc oxide. So that is what we are looking for as a word equation. So if I show the model answer, it's the exact same. Question 9. Now, from the reaction above, this one over here, you've been asked to rewrite the reaction twice, this time using the chemical symbols. The first time you write it, you need to put it as an unbalanced equation, simply replacing the words from the first equation with their chemical symbols. So, we know we've got zinc, and the symbol for zinc is Zn. We know it reacts with oxygen, and oxygen exists as O subscript 2. And then we'll turn off the subscript. And what they react together to form is this product, zinc oxide, ZnO. So we're just going to put it here, Zn for zinc, O for oxide, keeping in mind the capitals tell us it's a new element. Now, the second time we write it, we have to write a balanced equation. And what this means is that the number of atoms of each element stays the same on both the left-hand side of the arrow and also the right-hand side of the arrow. Also, add the state symbols as well. So, if we just copy that same equation that we had up here down below, this is what we get. this time we have to balance it. So to balance it, what we're first going to do is, if you consider how many oxygens we have on the left-hand side of this arrow, there is 1. If you now look on the right-hand side of this arrow, what I've highlighted, you can see there is 1 oxygen as well. So I would classify the zinc. I would classify the zinc as being balanced because there is 1 on each side. Then we can move on to the oxygen. We can see on the left-hand side of this arrow, you have 2 oxygens, whereas on the right-hand side of this arrow, you only have the 1 oxygen. So to actually balance equations, there are some tricks to it. When we balance equations, we cannot put our numbers anywhere. They can only exist at the start, so here, here, or here, of each of our components. So, if we have 2 oxygens on the left, and we need to have 2 oxygens on this right-hand side to make the oxygens equal, what we're going to do is put a 2 up the front. Now what this does, it now tells us there is 2 lots of oxygen, because everything that is connected and right after the coefficient, so the number up the front, means it is multiplied. So we now have 2 lots of oxygen on the right, and we have 2 lots of oxygen on the left of the arrow. So you could say that the oxygen is now balanced. Now we have to go back and take a look at the zinc. At the start, zinc was balanced with 1 on the left and 1 on the right. However, by adding the 2 now, on the right-hand side, we have 2 lots of zinc, so 2 lots of zinc, whereas on the left, we only have 1 zinc atom. So to balance off our zinc, all we have to do is put a 2 at the front of this zinc. So if we look at this equation as a whole, it tells us we have 2 zinc on the left, we have 2 zinc atoms on the right. We have 2 oxygen atoms on the left, we have 2 oxygen atoms on the right. So as a result, that is now, number 2 is now a balanced equation, which is exactly what the question wanted. The only thing we're now missing is your states symbols as well. So zinc, we know, is our metal, and our metal is solid. So we're just going to go ahead and put a little S there. Oxygen, we know, is a gas. So we're going to put a G. And zinc oxide here, it is still going to be a solid because it's a protective layer of solid. It tells us up in the question. So we're going to go ahead and put an S there. And that, Year 10, is how you solve question 9. So if I show the model answer, it'll be the exact same. Moving on to question 10. Using your equation, so the ones up above here, explain why the reaction between zinc and oxygen is a composition reaction. So, if we review what a composition reaction is, it is that a reaction that requires 2 or more reactants that form a single product. And we know that this equation, or this reaction, it starts with 2 or more reactants and it gives us a single product. So you could actually say that this reaction follows the general form of a composition reaction. So A plus B gives you AB. It has 2 reactants, so zinc plus oxygen, that combine to form a single product of zinc oxide. Now, that is a general overview of what composition reactions are, so combining reactants together. Now we move on to what decomposition reactions are. So, To produce ammonia by the Haber process, high temperatures are used to speed up the reaction. The problem with this is that the heat causes some of the ammonia to break down into nitrogen and hydrogen again, keeping in mind that ammonia is made up of hydrogen and nitrogen. So, one way of maximizing the amount of ammonia produced is to continually extract it from the reaction chamber and cool it to a liquid form. So what this means is that by making a batch of ammonia, when that's ready to remove it, the reaction can keep taking place without the ammonia breaking down again. So we get maximum output with little disruption. The breakdown of ammonia to nitrogen and hydrogen is an example of a decomposition reaction. This is when a single reactant, so what you start off with is one ingredient, so AB. This is when a single reactant breaks down into two or more products. So if we have one reactant, so AB, it undergoes a chemical reaction to form A and B. So it breaks down this time. So if we look at this animation on the side, let's just wait for it to start from the beginning. So just here, we've got two lots of ammonia, energy is added, then the atoms break down again. And then they combine again. The ammonia is here, two lots of NH3, it undergoes the breaking down into hydrogen and ammonia, then it recombines. So it's an entire cycle. So, question 11 asks us to write a balanced equation for the decomposition of ammonia, including state symbols. So, if we look at this animation up here, we can see there is two lots of NH3. So NH3, and there's two lots. So we're going to go ahead here and write two lots of NH little 3, and we know ammonia is a gas. And we then know it has to break down to form N2. So we've got N2 here as a gas. So N2 as a gas. And let's wait for this animation. Then we have three lots of hydrogen 2, so H2. So three lots of H2 gas. So if we were to break it down, and by doing all of that, we count how many nitrogens are on the left. So we've got two nitrogens on the left, two nitrogens on the right. We have two lots of H3, so 2 times 3 is now 6. So we have 6 hydrogen on the left. 3 times 2 is 6 H, so 6 hydrogens on the right. So this equation is now balanced, and this is the equation for the decomposition of ammonia. Question 12 relates directly to this video that's here. It's a quick clip that shows the decomposition reaction of an explosive material, and it was just a space for you to record some notes. Now, talking about those explosive materials, an example is the explosive produced from ammonia called nitroglycerin, and it's the key ingredient that's used in dynamite. This highly dangerous liquid breaks down to produce a rapidly expanding mixture of gases. So we've got nitroglycerin liquid, breaks down to form nitrogen gas, carbon dioxide gas, water vapor, and oxygen gas. So here we have our nitroglycerin liquid, because it tells us it's a liquid. It breaks down to form nitrogen gas, so 6 lots of nitrogen gas, 12 lots of carbon dioxide, CO2, gas, that's told us there. Water vapor, so water, H2O, so 10 lots of that. Because it's a vapor, it's in a gas form. And oxygen, O2, as a gas, shown by the G. So notice that the equation has the general form of a decomposition reaction, where you have one reactant forming multiple products. So on the side here, you can see that there is a dilute solution of nitroglycerin, and it's been used to treat certain heart conditions by dilating the blood vessels, which means it releases the pressure and allows them to become wider. Now, given the info that's above, question 13 asks, how many gas molecules are produced by the decomposition of 4 molecules of liquid nitroglycerin? So, we know there are 4 molecules of the nitroglycerin. As a result, how many gas molecules? So all those that are in a gaseous state. So that includes your nitrogen, carbon dioxide, water vapor, and oxygen. So all we have to do is add the coefficients together. So the numbers at the very start. So we've got 6 for the nitrogen, plus 12 for carbon dioxide, so that's 18 so far, plus another 10 for the water, so that's 28, plus there's a 1 in front of this oxygen because there's only one lot of it. So we said there was 6, 12, 18, 28, 29 molecules of 29 gas molecules are produced. Question 14. Using the equation that's just above here, suggest a reason for the explosive nature for this reaction. A hint is given to you. You might refer to both the number of molecules produced and their state. So, what we are considering here is that the reactant being a liquid and the products being a gas. Keep that in mind. So molecules in a liquid take up much less room than molecules in gases, which have a lot of empty space between them. And in this case, just 4 molecules of liquid convert to 29 gas molecules. So there's very much more space being required for the products of this reaction than the reactants. So keep in mind, you only start off with 4 molecules, you end up with 29 molecules. So you end up with more than you started with for the molecules and how much space it takes. So since this reaction happens very quickly, the gases produced expand very rapidly, which is also seen as the explosion. So the expansion of the gas is what we know as the explosion. Question 15. Based on the info about our nitroglycerin up here, select all of the decomposition reactions that we know of, given the formula AB breaks down to give you A plus B. So, if we look at this first one, 2 molecules of H2O liquid break down to form 2 lots of hydrogen gas plus oxygen gas. That could be one. If we look at this one here, CH4, methane gas, plus 2O2 gas, break down to form CO2, so carbon dioxide gas, plus 2H2O gas, so water vapor. It cannot be this one because you start with 2 reactants, and we know decomposition reactions are starting with 1 reactant, so it cannot be this one. With our next equation, we have 2 molecules of Fe2O3 solid, which reacts with 3 lots of carbon to give you 4 lots of iron solid plus 3 lots of carbon dioxide. We also know that a decomposition is not this reaction because you start with 2 reactants and you end with 2 products, so it cannot be this one here. The last response, you've got 2 molecules of KClO3 solid, which breaks down or it reacts to form 2 lots of KCl solid plus 3 O2 gas. This is also a decomposition reaction because you're going from one reactant to multiple products. So I'll just show the answer here. Question 16. Now, when many metal carbonates are heated, they decompose to form a metal oxide and carbon dioxide gas. For example, MCO3 solid breaks down to form MO solid plus CO2 gas, where CO2 is carbon dioxide and M represents your metal. So this one just means it's your metal. CO3 is carbonate, so your metal carbonate. Predict the product of the decomposition of barium carbonate. So instead of the M here, if we replace it with Ba, what we would end up with is every time there's an M, we're just going to replace it with Ba. So this one would be BaCO3 gives you BaO plus CO2. So out of all of these reactions, what you would end up with is you would end up with BaO for this one here, and also carbon dioxide gas. Now question 17. What we are looking for here. Let me just read through the instructions. Nitrous oxide, N2O, also known as laughing gas, decomposes when heated above 577 degrees Celsius. This reaction produces nitrogen and oxygen gases as well as a lot of heat, making it useful as a rocket propellant. Now, for the activity itself, step 1, balance the equation for this reaction. So to balance it, remember, we look at the reaction. So, with what we were doing earlier, let's start by breaking down what we currently have. What we can see here is on the left-hand side of this arrow, we have 2 lots of nitrogen, so 2 lots of N. On the right-hand side, we can see we've got 2 lots of N, so the nitrogen looks pretty good so far. Now for the oxygen. On the left-hand side, we have 1 oxygen, whereas on the right-hand side of this arrow, we have 2 lots of the oxygen. So oxygen isn't balanced. Now, one way we can quickly balance that is if we went ahead and put a 2 in front of our N2O, let's see what it now gives us as our reaction. We now have 2 lots of O on the left. We still only have 2 lots of oxygen on the right, so oxygen now looks pretty good. Now that we've got a 2 at the front of this equation, it now means everything behind it is multiplied by that number, so 2, which now means we have 2 lots of N2. So it means 2 times 2 is 4 nitrogens, whereas on the right-hand side, we've only got 2 lots of nitrogen. So the easiest way to balance that is going to be, let's put a 2 in front of that nitrogen. So let's try this equation again. Left-hand side, we have 2 lots of N2, which equals 4 nitrogens on the left. On the right-hand side, we have 2 lots of N2, which is 4 nitrogens on the right. So nitrogen's looking good now. And for oxygen, we have 2 lots of oxygen on the left, and we have two lots of oxygen on the right because we didn't put anything in here, which means you can either leave it blank, which just means it's 1, or if you just want to make it really clear, you can put a 1 in this space just to clear that up. So that's step 1 done. Now we've balanced that equation. Step 2, of this question tells us, drag the atoms from the reactant side, so the left-hand side, to their correct locations in the product side to make sure the equation is balanced. So, what it tells us is we have to drag these products over. So the red and the blue represent different components. So it tells us we know one of these is one of these. So one of these molecules is representing one of these. We know that this molecule has 2 lots of nitrogen to 1 oxygen. So there was going to be 2 nitrogens available for every oxygen, which tells us your nitrogen is the blue ones and your oxygen is the red circles. As a result, if we have to drag these over to this side, we now know we have 2 lots of nitrogen. So we've got nitrogen is blue, so 2 lots of N2. So N2, that's the first lot. N2, that's the second lot. To 1 pair of oxygen atoms, whereas your oxygens are red. So if we drag these over, that is what your equation and reaction should look like. So I'm just going to show the answer that should have been here, which is the exact same as what I gave. Now, question 18. Briefly summarize the difference between composition and decomposition reaction. Now, you're given a diagram on the side here to help you out as well. And what we now know is that a composition reaction starts with 2 or more reactants that join to end up with a single product. Whereas a decomposition reaction, you could see it as the opposite, but what it is, it's a reaction that starts with a single reactant, so one starting point, that breaks down into 2 or more products that we can see here. So to simplify both, a composition reaction is A plus B gives you AB, whereas a decomposition reaction, AB breaks down to give you A plus B. So an example I was giving some of the students was for a composition reaction. If you're at home, how would you make chocolate milk? You would use some chocolate syrup, so A, plus milk, B, to give you chocolate milk AB. An example for a decomposition reaction could be if you are taking apart an omelette just to see what the chef has used in it. So you're presented with an omelette. You can see that it is made up of, or it breaks down into eggs, a bit of mushrooms or whatever else you like in it, and maybe a bit of milk to help it out. So composition reaction, where you're adding reactants together to form a single product. Decomposition reaction, you start with a single reactant that breaks down to form multiple products. So if you haven't already, please use this video to help you go back into your responses, change them up if you need to, and then just down the bottom there will be a little button in blue that says, "I'm finished, show my teacher." So please make sure you go through all of this.